All right. Testing sound like this. Okay. So we should be fine now. All right. So, number theory, we're going to start with, we're going to be using two books, as I said before. So, one of them is a university level introduction to number theory, a book that I like very much. But the second one is called Introduction to Number Theory. And this is by the guys at Art of Problem Solving, the guys responsible behind that series. Sure, they go by AOPS, Art of Problem Solving. I like this series a lot. It's a very problem solving based approach to stuff. Problems are very intuitive. They're down to earth, less theoretical, but they do teach you the basic concepts, and they definitely teach you how to approach problem solving, how to solve complicated problems as well as simple ones. So I will start here, and then we'll transition slowly into using the university book as well. So introduction. So this is going to be number theory. Now, the introduction starts with a talk about integers and what they are and how do you think about integers. So, one way in which um, the author of this book, Matthew Crawford, describes integers is numbers that we use to count things. Okay, very simple. So you can use integers to count things. So you can have one apple, 2, 3, 5, and we augment this counting numbers by their negative versions, maybe 4, maybe 7, and a 0 as well. And we call these integers. Now, so this will be our integers, sometimes written as this in mathematical notation. If we just take the positive ones, 4, etc., we get what's called the natural numbers, sometimes written this way as n. These are, of course, the numbers for counting. And then if we use and some people, when they say natural numbers, they include the 0. I usually don't. If I want to include the 0, I will say I have the 0, the set containing the number 0, as well as my natural numbers. Okay, so this is the same thing as the naturals, except it has 0 as well. So that's what this is, etc. Number theory deals largely with this object. It's about the integers. But it turns out that when we're talking about integers, it is usually enough to just consider this set, the 0 and the naturals. A lot of the things that you prove that are true for this set will be true for integers. There's a simple extension usually from the naturals to the integers. Usually, again, not often, but this is most of the time. Okay, so a number that has at least a single digit after a decimal point is not an integer. So a number like this that has at least one digit after the decimal point cannot be an integer because we cannot reach this number by counting from some starting point, up or down, using ones. So let's say I start at 0, and now I'm going to count in ones. So I add a 1, I get 1. I get a 1, I get 2. I get a 1, I get 3. There is no way I could reach this number by starting from some number from here, from some natural number, and counting up or down in terms of ones. So this cannot be an integer. Okay, so the numbers that have at least one digit after the decimal point are not integers. And again, to think of integers in simple terms, these are numbers we use to count things. Okay, and we can count forward or backward. So when we count forward, we're using the natural numbers 1, 2, 3, 4. When we count backward, we use their negatives: -1, -2, -4, and 0 to count the non-existence of something. So I have 0 of something, I don't have it. Okay, now we can, of course, make new integers out of other integers. We have operations for that. If I have 2, I can add 4 to it and then get another integer, right? If I have -4, -4 is also an integer, and I add them and I get -2. I can take 2 and subtract 4. Well, you say subtraction is, of course, addition. And this is the same thing. It's -2. I can do 2 minus -4, and we all know this is 6. So we can multiply. We can do 2 times 4 and get 8. We can do -2 times -4 and also get 8. So I can do a lot of things. I can combine integers in various ways and get new integers. Okay. So let's take a look at the products of some integers with themselves. Okay. What does that mean? Product of an integer with itself. Let's pick an integer. How about 4? And let me look at the product of 4 with itself. What do I get? I get 16. What about 1? 1 times 1 is 1. What about 2 times 2? Well, that's 4. Now, the question is this. Let's find every integer less than 100 that is a product of some natural number with itself. Again, what was a natural number? A natural number, a set of natural numbers, was the set of the numbers we use to count things. Now, what we want to do is we want to find the set of all the numbers, all the integers less than 100. So all the integers that are less than, let's say, or equal to 100, that are a product of some natural number with itself. Now, you might start by saying, well, what about 99? What about 98? What about 97? These are all less than or equal to 100. Are they a product of some natural number with itself? And you might go down this route, but it's a lot simpler to start from this set here, to start here with these numbers. Let's take the first one. I want to know what is its product with itself. It's 1. Oops. It's 1. Is 1 less than or equal to 100? Yes. We put it in our set here. We put it in our final answer. Let's go to 2. 2 times 2 is 4. Is that less than or equal to 100? Yes. 4 belongs here. 3 times 3, that's 9. Yes, it's less than or equal to 100. 4 times 4, 16. Yes. 5 times 5, 25. Yes. 6 times 6, 36. 7 times 7, 49. 8 times 8, 64. 9 times 9, 81. 10 times 10, 100. So these are numbers, natural numbers, less than or equal to 100, that are a natural number multiplied by itself. That's what they are, right? 49 is a natural number multiplied by itself. Now the question is there another one? Well, if I took 11 times 11, well, if 10 times 10 is 100, 11 times 11 will definitely be larger than that. And we're not interested in numbers larger than that. We're only interested in numbers less than or equal to 100. So we know we've covered all of them. This set of numbers is my answer. So what did we do? We took the opposite approach. Instead of asking ourselves, is 99 a natural number times itself? Is 98 a natural number times itself? We said, let's start with the smallest natural numbers, multiply them by themselves, write down the result. If the result is less than or equal to 100, we keep it. If not, we stop. We know we've gone overboard. Okay, moving on. When dealing with number theory, it is often useful to be able to visualize these operations. We all know algebraic properties of addition and subtraction, so we know how this is done. But how do you visualize this? Because, as I said, we can think of number theory really as counting up or down. So what did we do here? Suppose I have my 0, and I have my 1, and I have my 2. When I add 4, what am I doing really? So what I'm doing is I'm adding 4 ones. Okay, so let's do that. So when I add 1 here, I come to 3. The second one, I come to 4. Okay, the third one, I come to 5. And the fourth one, I come to 6. So notice I added 4 ones. I counted up from 2 4 times, and I got to 6. That's this expression. What about the one below it? We start from 0. Here's my 1, here's my 2. What do I do from 2? I count. Notice the negative 4. So I'm actually counting backwards 4 units. So when I go 1 unit left, I come to 1. 1 unit left, I come to 0. 1 more unit left, I go to -1. And 1 more unit left, I go to -2. And that's exactly what we have. And let me do a product as well. How do we visualize a product? Well, if I have my, let's say, 0 is here, 1 is here, 2 is here, what am I doing? I'm doing 2 times 4. 2 times 4. So 2 4s, right? 2 times 4, 2 4s. So let's do that. If I add the if I go up from here, what am I going to get if I do 2 times 4? Oops, a second. So that's 1 plus 1, starting from 0. I get plus 1 plus 1. And how many of these do I want? I want 4 of these, right? Because it's 4 times this. Whatever we counted up to from 0, and I want to do that 4 times. And if you do that 4 times, this is the second time I'm doing it. And if you keep counting this way, you will get your result. Okay. Another way to visualize this would be, here's your 0, right? And you want to count by 4s. So if I count by 4s, how many of these 4s am I interested in? 2 of them. So if I count by 4s, so plus 1, plus 1, plus 1, plus 1, that gives me the first 4. And then for the second 4, I do the same thing. Plus 1, plus 1, plus 1, plus 1. And that gets me, of course, to 8, which is what I have. Okay, and same with the -4. If I had -4 times 2, I would count backwards 2 4s, but it's negative. 2 negatives cancel, and it's the same procedure. So in essence, we're counting. That's what we're doing when we multiply or add. We're counting by 1. So you see that multiplication is really fast counting. Multiplying by 2 meant we were counting by 4s instead of by 1s. By individual pluses, we were counting by whole 4s. Here's 1 4, here's another 4. It's the same with exponentiation. If you do 2 squared, this is really a multiplication, so it's the same as this case. We're counting by 2s instead of by 1s. It's fast counting. Okay, now what is a perfect square? So the example that we did a minute ago, when we were looking right here, this example here, when we were taking an integer and multiplying it by itself, these numbers are called perfect squares. It's a number that is formed by taking some natural number and multiplying it by itself. That's the reason this is called a perfect square, is because we're multiplying this thing by each other. It's a square of n. So this is n squared. And this becomes perfect square. So to reformulate this question, we could have said, list all the natural numbers that are perfect squares that are less than or equal to 100. Well, 1 is a perfect square, 4 is a perfect square, 9, 16, 25, etc. 100. These are perfect squares. Now, you might have said, okay, what are all the perfect cubes? Well, if I want to know what the perfect cubes are, I need to multiply those integers by themselves 3 times. I know that 1 times 1 times 1, that's still 1. 1 is the perfect cube. 2 times 2 times 2, that's 8. 8 is a perfect cube, right? 3 times 3 times 3, 3 cubed, that's 27. 27 is a perfect cube. So these are my perfect cubes. They're formed by taking our natural numbers and multiplying them by themselves 3 times. And I mean, you can keep going. And in general, a perfect power, this is a generalization, a perfect power is a number that is formed by taking some natural number and raising it to some power p. So now this p can be anything you want. If you're talking about perfect squares, p will be 2. If you're talking about perfect cubes, p will be 3. Perfect quadruples, perfect whatever you want, perfect 10th power, so p will be 10. Essentially you're looking at all the numbers that are some natural number multiplied by itself some number of times. All right. Now, a simple set of examples and exercises, actually. So the first one says the following. It says, if we subtract one natural number from another, is the result always a natural number? Now, let's think about this. Let's suppose I have a natural number 4. And from it, I subtract a natural number 1. Is the result a natural number? Yes, it's 3. 3 definitely is a natural number. It's a number I can count with. But what if I took a natural number 1 and subtracted another one, 4? What would I get? I would get -3. Is that a natural number? And the answer, of course, is no, it's not. It's an integer, but it's not a natural number. So if I subtract two natural numbers, it's not necessarily true that the result is a natural number. In some cases, it will be, like in this case above. In this case below, it's not. Is the product of two natural numbers a natural number? Well, what are natural numbers? They're numbers from 1 to infinity, right? 1, 2, 3, 4, 5, etc. If I multiply two integers, first of all, is the result an integer? Yes, if I multiply 2 times 3, the result is an integer. There's no way I could get a decimal here. So the only way I would not get an integer, I mean a natural number here on the right side, is if my result was negative or 0, because those are the only two classes of integers that are not in my naturals, the negatives or the 0. Well, now think about it. If you take two natural numbers and multiply them, is there any way that the result would either be 0 or negative? No, right? If these two are non-zero, their product is non-zero. If they're both positive, their product is positive. That's it. So the product will be a natural number. What about division? What if I divide two natural numbers? Well, let's take 5 and divide by 7. This is not even an integer. So it's definitely not a natural number because it's not even an integer. So division does not guarantee that we stay within the bounds of natural numbers. And here's an exercise that says the following. It says we have 100 and we have 200. Find all perfect squares between these two numbers. So what are perfect squares again? A perfect square is a number that is formed by multiplying a natural number by itself. We saw them, right? 4, 16, 25, etc. Now I want all perfect squares between these two. 100 is a perfect square. It's 10 times 10. Right? Now, how do I start from 100 and find all the perfect squares? Now, you could approach this directly, and you could say, is 101 a perfect square? Is 102 a perfect square? 103, etc. But what we'll do is this. I know that 10 times 10 is 100, right? So the next perfect square, the next perfect square after 100 has to be 11 times 11. There's no other choice. There's nothing smaller. There's nothing in between 10 and 11. So the next perfect square has to be 11 times 11, and that, of course, is 121. The next one has to be 12 times 12. The next one has to be 13 times 13. The next one has to be 14 times 14. Right? And as you go through these multiplications, at one point you will get a number that is larger than 200. And that's when you'll stop. And everything that you get on this right side of the column here, these will form your answer. Okay? So 10 times 10, 11 times 11, 12 times 12, right, etc. And at some point you stop. As soon as you go above 200, you stop. Again, so this solution method relies on the realization that the next largest perfect square from 100 has to be 11 times 11, because 100 is 10 times 10. The next one is 12 times 12. The next one is 13 times 13, right? So 169, etc. And at some point, as you pass 200, you stop. I hope that makes sense. Again, if it doesn't, try to do it yourselves, first of all. If that still doesn't make sense, ask in the Discord channel, and we'll help. So let's talk about integer multiples now. Suppose we counted up from 0, but instead of counting every integer, we only counted every fourth. So what do we get? If I'm counting every fourth integer, I'm counting by fours. So I get 0, I get 4, I get 8, I get 12, etc. So I'm going in fours. How many fours must we add together to equal each of the following? And the following being 12. How many fours do I need to add together to get 12? Well, we know the result is 3, right? This is 3 fours. What about 28? How many fours? Well, we know I need 7 fours to get 28. What about 44? And of course, we know we need 11 fours to get 44. Now, starting from 0, we can count by 2s up to 50, right? So 0, 2, 4, etc., up to 50. This is the set of numbers I'm working with. Which of the following integers would be in this list? So there, I could ask you that question. I could say, is, for example, 30 in this list? Is 30 in here? How would you know? Well, you would say this. You would say, I know that list of numbers is formed by counting by 2s. Every one of those numbers is some multiple of 2, right? So this one, 0, is 0 2s. 2 is a single 2 from 0, starting from 0. 4 is 2 2s. And so asking whether 30 is in this list is the same as asking how many 2s do I need to get to 30. So I can write that question this way. I can say, how many 2s would I need to get to 30? And what this comes down to is this, can I divide both sides by 2? In other words, if I did both division by 2 on both sides, I want this question mark to be a natural number, right? To be a natural number or 0, to be positive integer or 0. See, 0 2s, 1 2s, 2 2s. And luckily, if I divide 30 by 2, I get 15. That is a positive integer, which tells me I need 15 2s to get to 30. So yes, 30 is in this list, but what if I asked you the following question? Let me erase this guy here. Let's increase the size of the eraser. So I ask you whether 45 is in this list. Is 45 in this list? So that's the same question. We say, how many 2s do we need to add starting from 0 to get to 45? So how would I solve this equation for the question mark? Well, I would divide both sides by 2, right? 45 by 2. And if you try 45 by 2, you will find that it's not divisible by 2, right? 22 and a half. It's not divisible by 2. So there is no integer, positive integer number of 2s that I can add on top of each other to reach 45. So 45 cannot be in this list. Okay? That's the way you think about this question. Okay, a similar kind of question, a similar question asked differently is this. So let me draw a picture for you. Erase the stuff. And now we have a list of numbers, or a list of dots, I suppose. So we have dot here, dot here, dot here, dot here, etc. These are numbered. So 1, 2, 3, 4, and they go all the way to 10. We'll put a thing here and put 10 here, and we have a second row of numbers that start, or of dots that starts from the 11th dot, 12th, 13th, 14th, and goes to 20. So we have 20 dots in 2 rows. Okay, so each time you place a dot, label it with the next smallest counting number that you haven't already used as follows. So here's our picture. Now, suppose you continued adding rows to your grid until there were 100 rows. Okay, so what is that really saying? I'm going to add a row to my grid each time until I have 100 rows. Right now I have 2 rows. So imagine there are 100 of them. That's the point. Now, which of the following integers would label a dot at the end of the row? So notice here is the end of each row. Here is an integer that labels the first dot at the end. Here is the integer that labels the second dot at the end. So the question is, if I have 100 of these rows, now I'm going to give you some integers and I'm going to ask you, do they label a final dot in some row? So let's start with 70. Does 70 label a final dot in some row? Now, if you're quick and you look at this pattern, you realize that the first row ends with a 10, 1, 0. Second row ends with a 20, 2, 0. If you continue this pattern, you realize that the third row will end with 3, 0, a dot 3, 0. That will be the third row. And now my question to you is, what would the seventh row end in? What dot would be labeled in the seventh row? And you realize that it's 70. So 70 is, in fact, 70 does label a final dot in the seventh row. What about 75? Definitely not, because if seventh row ends with a 70, in the eighth row, we're going to have what? We're going to have 71, 72, 73, 74, 75, etc., right? And other dots. So 75 does not label a final dot. What about 99? Well, again, if you think about this, the 100th row, the last row, what will be the label of the final dot? Here is a final dot right here. Its label is going to be 100, right? So the 99th dot is going to be right next to it, to the left of it. It is not a final dot. Okay. And so on, and we can keep on going in this manner. And then we can ask the same question, and you'll realize that the final dots, that the labels of the final dots all have zeros at the end, right? 10, 20, so 21, 22, 23, 24, blah, 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 30, 40, 50, 60, 70, all the way to 100. So all these final dots have a zero at the end of them. And now if I told you, keep going, increase the number of rows, 200 rows, 500 rows, so it doesn't matter, however many rows you have. If I give you a number and ask you whether it labels a final dot, if it doesn't end in a zero, the answer is no. Okay? I hope that makes sense. So moving on, let's take a look. So in this example also, you might have noticed that if we take 10, notice that, by the way, each row, we're counting by how many? So we counted by 10, right? First row 10, second row 20, third row 30. So we're counting by 10 each time. So we're looking at multiples of 10. So 1 times 10. Second row gives us 2 times 10. Third row gives us 3 times 10. And this was 10. This was 40, right? If I do, I'm sorry, 2 times 10, that's 20. 3 times 10, that's 30, etc. So the thing to notice is that multiples of 10 have a 0 at the end. And you can see if you look at these rows, you'll see why, right? 1 through 10, 11 through 20, 21 through 30. As we count in tens, the resulting number always has a 0 at the end. This will become very important when we start doing some interesting number theory. The fact that multiplication by 10 gives a 0 at the end. That's something to remember. All right, let's do some examples, some exercises rather. So the first one says, is 22 a multiple of 4? Is 22 a multiple of 4? In other words, what does that mean? 22 a multiple of 4. So to rephrase this question, you might say, is there some number that I could multiply by 4 and get to 22? In other words, can I count by 4s some number of times to get to 22? And again, you say, is there some number that I can multiply by 4 by and get to 22? If I divide both sides by 4, I realize that the result is not an integer. This number here is not a natural number. It is not a positive integer. The answer is no. Okay, 22 is not a multiple of 4. Is 63 a multiple of 9? 63 of 9. So 63 of 63, we want to know if it's a multiple of 9. So again, you say, is there some number of times I can count by 9s and get to 63? Okay. So now you might say, all right, well, I know if you just think of the basic multiplication table, right? You know that 5 times 9 is 45. Adding one more 9 to that will give you 54. And adding one more 9 to that will give you 63. Right? So yes, the answer is yes. How many 9s did we count? Well, let's draw that number line. How many 9s did we count by? Well, 1 9. Here's my 0. So I counted by 1 9. I reached a 9. 2 9s. I reached 18. Right? 3 9s. I reached 27. 4 9s. 36. Another 9. 45. Another 9. 54. And finally, one more 9. And we got to 63. How many 9s is that? 1, 2, 3, 4, 5, 6, 7. So you say, yeah, if I count by 9s 7 times, I get 63. So 63 is in fact a multiple of 9. Now again, you know your multiplication tables. You could have instantly said, oh, I know 7 times 9 is 63. The answer is yes. The key is just understanding that what you're doing is you're counting by 9s. And you're just saying, if I count 7 of these 9s, I get 63. That's all. Is negative 18 a multiple of 6? So is there a number of times I can count in 6s to get negative 18? You say yes. If I go to the left by 6s 3 times, I get negative 18. So the answer is negative 3. Yes. Is 23 a multiple of negative 13? So 23, a multiple of negative 13. Here's our 0. So I'm counting by negative 13s, right? The answer should be positive. So I should be definitely counting some negative amount of times. So I'm moving to the right. Well, if I count by a negative 1 of these guys, I get 13. And if I do negative 1 more, I get 26. Oh, I overshoot. So the answer is no. There is no integer amount of times I could count by negative 13s to get to 23. So the answer is no. 23 is not a multiple of negative 13. To the next question. The next question says, find the 10 smallest positive multiples of 7. 10 smallest positive multiples. Well, again, if instead of trying to guess what these numbers are, well, we want smallest multiples of 7, right? Well, let's write them out. Positive multiples. 1 times 7 is 7. I know there can be nothing smaller than this because if I did 0 times 7, I'd get 0, and that's not even positive. And I keep going up. 2 times 7. 3 times 7. 21, of course. 4 times 7. 28. 5 times 7, etc. And I'm interested in the first 10, so I know that the last one will be 10 times 7, which is 70. I know there's nothing in between. How do I know that? Because look at these integers. They're going from 1 to 10. There are no more natural numbers in between those. These are my smallest natural numbers. So that if they are the smallest, these multiples of 7s are the smallest. Find the 10 smallest positive multiples of 10. So it's the same procedure, right? 1 times 10, 2 times 10, all the way to 10 times 10. Find the 5 smallest positive multiples of 13. 5 smallest. So we do 1 times 13, 2 times 13, 3 times 13, 4 times 13, 5 times 13. There they are, 5 smallest positive multiples. Find the 5 largest negative multiples. So let's think about this. What is the, so remember, when you have the number line here, and this is your 0, -2 is smaller than -1. -3 is smaller than both of them. So as you go to the left, even though these digits here are increasing, because these are negatives, the overall numbers are decreasing. So the largest negative multiple of 13 is -1 times 13. The next largest one would be -2 times 13, and then -3 times 13, right? Because -1 is the smallest, is the -1, excuse me, is the largest negative integer. If it is the largest one, then this multiple is the largest one. This is the -2 is the second largest negative integer. So this multiple is the second largest. And so on. Next problem reads as follows. Okay, find a list of the first 10 positive multiples of 4 and a list of the first 10 positive multiples of 6. Find the smallest positive integer that is a multiple of both of them. Okay, let's write out both lists. 10 positive multiples of 4. Okay, so that's, of course, 4. That's 1 times 4, 2 times 4, 3 times 4, 4 times 4, 5 times 4, 6 times 4, 7 times 4, 8 times 4. Then we have 9 times 4, and then finally we have 10 times 4. Here they are. Second list, positive multiples of 6. So there's 1 times 6, 2 times 6. It's 2 times 6. Now, do I need to go on? The question says find the smallest positive integer that is in both of these lists. Well, I know that as I fill more integers in, they're only going to get larger here in this bottom row. But I've already found an integer that is in both lists. And I'm only interested in the smallest such integer. Whatever comes after here is going to be larger than 12. So I stop at this point, and I say 12 is my answer. So 12 is both a multiple of 4. How many 4s? 1, 2, 3. And it is a multiple of 6s. How many 6s? 1, 2. And we see that some numbers, some integers, can be multiples of 2 different numbers. Different multiples of 2 different integers. Last question. Find the smallest positive integer that is a multiple of both 4 and 7. 4 and 7. Smallest positive integer. Well, look, I already have multiples of 4 written out. It's this first row right here. Let me write down the multiples of 7. So that'll be 7. That'll be 14. Do any of these match yet? No. 3 times 7, 21. No. 4 times 7, 28. There it is, 28. Right? 28. I know that as I fill this row, numbers are only going to get larger. I'm interested in the smallest integer that is in both lists. The answer is 28. So when we count by 4s, how many of them did we have? 1, 2, 3, 4, 5, 6, 7. We had 7 4s, and we got 28. When we count by 7s in the second list, how many 7s did we have? 1, 2, 3, 4, and we got 28. And oh, look at that. Beautiful. That's our commutative property of multiplication. Okay. In this case, we just thought about it as counting by a certain number, but of course, it's the commutative property of multiplication in this case. Okay. So I'm going to post some questions now because this is actually, give me a second. Let me take a look at the material here. Let me see how far I want to go. All right, so let's talk about divisibility of integers now. We talk about multiplication, right? Multiplication is just fast adding. Now, divisibility, of course, dividing numbers is the opposite of fast adding. So we could say, what is 4 over 2? In other words, is 4 divisible by 2? And the answer is yes. This is an integer, of course. 2 times 2 is 4. 5 over 2. Can I count by 2 some number of times to get to 5? Of course not. This is not an integer. 12 by 3 is an integer. It's 4. 14 by 3 is not. I cannot count by 3s and get to 14, starting from 0, of course. We're always starting from 0. Negative 35 over 7. Yes, we can. If I start from 0, count by 7s, how many of them do I need? Negative 5 of them. If I do negative 5 of them, I'll get to my desired number. And let me do just one more maybe. Or let's do this one. What about a third plus 2/3? We know how to add fractions. This is 3/3, which is, of course, 1, an integer. Lastly, 22 over 5 minus 19 over 5. Again, this is 3 over 5, which we know is not an integer. Okay. So they're not divisible. This is testing divisibility. Now we say that an integer m, let's formalize what we just did, because it seems like I'm just doing arithmetic, but there is formalization to this. Formalization is this. We say that an integer m is divisible by an integer n. So m is divisible by some other integer n when this quotient is an integer. So as an example, if I set m equal to 4 and n equal to 2, then let's look at 4 over 2. This is my quotient, right? M over n is 4 over 2. Is this an integer? Yes, it's 2. So we say m4 is divisible by 2. Another example is if I let m be 5 and I let n be 3, and then I look at the fraction, the ratio, 5 over 3. Is this an integer? No. So we say m is not divisible by n in this case. Now here comes an important note. We know that 0 times anything is 0, right? So 0 is a multiple of every integer. Think about it. Whatever you plug in for n, 0 times that is going to be 0. So the 0 is a multiple of any integer n. What multiple? 0th multiple. 0 times that. And that n will give me 0. Okay? But n over 0 is not defined. We know that we cannot divide by 0. So no integer is divisible by 0. Why? When did we say m is divisible by n? When this ratio was an integer, right? But if I cannot divide by 0, this ratio cannot be formed. I cannot form this ratio. So this number here cannot be divisible by 0. I cannot divide by it. So no number is divisible by 0. Okay, so as a technical aside, so 0 is a multiple of every n, but no n is divisible by 0. Okay. And let's do a couple more example exercises from here, and we'll stop. So determine which of the following integers are divisible by 6. So very, very simple. 11. Is this divisible by 6? Of course not. One way to think about it that I kind of like is I know 12 is divisible by 6. How many 6s do I have to count to get to 12? 2, right? So there's 1 6. There's 1 6, gets me to 6, and another 6 gets me to 12. Now, if you tell me that 11 is also a multiple of 6, then because 11 is less than 12, I should be able to count some less number of 6s and get 11. I know 2 6s get me 12. I know 1 6 gets me to 6. Between 1 and 2, there are no more number of 6s I could count. So there's no way I could reach 11. So 11 is not a multiple of 6. So this is, again, one way to think about this question in terms of counting by that certain number, counting by 6s in this case. All right, is 35 divisible by 6? Well, it's the same thing, right? You tell me, starting from 0, I know that if I went 6 times, 1, 2, 3, 4, 5, 6, I would get to 36, right? That's 1, 2, 3, 4, 5, 6. Counting 6s. 35 is right next to 36, 1 unit to the left, which in principle means that if 35 is in fact some number of 6s, it has to be less than 6 6s, because 6 6s is 36. But 5 6s is 30. So there are no more natural number of 6s between 5 and 6 of them. So 35 cannot be some natural number of 6s. It is not a multiple of 6. Okay? All right. Is 100 divisible by 12? So we have 100. And the question is this divisible by 12? Can I count in terms of 12s and get to 100? Okay, well, you think about it. Let's think about the nearest number that we know is a multiple of 12. Okay, what is that number we know that is a multiple of 12? Well, 120, for example, if I do 12 times 10, I get 120, right? I know that if I start from 0 and go 10, count by 12s, 10 times, I get to 120. So here would be my 120. I've counted 10 times. 1, 2, 3, 4, 5, 6, 7. Well, let's just assume there are 10 of these guys here. And I'm counting by 12s, right? Each time. If I move 1 12 left, 1 12, instead of 10 of them, I count 9 of them. What do I get? 120 minus 12 gives me what? 108. 108, right? That's still not 100. I still have place to go. So what if I move to the left 1 more 12? Well, 108 minus 12 is less than 100. Right? I don't reach 100. It's less than 100, so 100 cannot be a multiple of 12, right? We started from the one that we knew 10 times. There it is. It is above what we need. We need 100. We have 120. So we say, okay, let's start counting back 12s and see how many times we need to count back 12s. Well, if I count back 112, I get 108. If I count back another 12, I get something less than 100. So there's no natural number of 12s I can count to get to 100. So no, 100 is not a multiple of 12. So it is very, very simple. We haven't really done any serious number theory, but it is interesting to think about multiplication in this way, that you're counting by some number. You're counting quickly by some number, by 12s, by 6s, by 10s. You can count by 1s if you want, but that's no longer quickly, right? That's just counting. And so on. So I'm going to stop here, and then next time we'll pick up with divisors. We'll start talking about when a number is a divisor of another number, and then we'll start doing some, we'll do our first competition problem with number theory, and then we'll get into primes and composites, and that's when number theory will really take off. Once we introduce primes, then the beauty of this subject really kicks in. All right, guys, if you have any questions, if any of this didn't make sense, do post questions on the Discord channel, and I'll be happy to answer them. All right, see you guys later.